the screen, and if I go to the next slide, it's also good. You see all the people. All right, fantastic.
Yes.
So thank you so much, Arlene, for the invitation and for the nice introduction. So as Arlene mentioned, my name is Kianoosh, and I'm an assistant professor in the Department of Mechanical Engineering at University of Texas at Dallas. So we are a team of a couple of PhD students and postdoc here. So we have a wind wave tunnel, as you can see in the picture here on the video here, technically. So this wind wave tunnel is around 15-meter long, a little less than that, like 2-meter high and 1 meter wide. So we use this wind tunnel to do our experimental work and measurements, and we use this experimental work to see how these waves are generated and how they are interacting with the atmosphere and the ocean, with the end goal of having improved weather prediction, especially under hurricane conditions. So the typical research that we do in the lab is considered in a three different direction. The main direction, as I mentioned, is to study the atmosphere and ocean interaction in order to have a better understanding of how small scale processes at the surface of the ocean affect the structure of the flow above the surface or below the surface. And that knowledge can be used to develop some new model and parameterization for the larger scale weather forecasting. Another direction is related to that, but it's more kind of on the engineering side of the problem. So we are looking at how these waves that are generated at the surface are interacting with different structures. And that structure can be an oil rig, kind of, it can be a wind turbine, offshore wind turbine base. It can be wave energy converter devices that are there. It can be coastal structures. So any interaction that happens in the ocean between waves and the structure, it would be of our interest and be a study. So here you see offshore wind turbines and also some wave energy converters that we do a study these type of energy conversions. So and the third direction is anything else that would be related to the fluid mechanics. And here is an example of drug delivery. So that was a work that we tried to have some drug delivery, vaccine delivery without using needles. And so it technically uses a high pressure medium to insert the drug or the vaccine particles into the skin, as the skin is a porous media, right? So we can inject the particles directly to the skin. So, but what today I'm going to talk about is something that affects all of us in a sense, right? Even if we don't think about it every day, and that's the ocean atmosphere and the storm that will be generated in the middle of the ocean. The ocean and atmosphere constantly exchange energy and momentum, and that will help to shape waves and storms and long-term climate patterns. Hurricane like Sandy on the right and Laura on the left are kind of some reminders that when the prediction of these extreme weather events are off, the impact can be huge. And the focus of our research, especially for the talk that I'm presenting today, is on improving the physics behind these predictions, and we want to start right at the air-sea boundary, at the ocean surface. So Hurricane Sandy is actually a well-known example where models struggled with the storm path, so they couldn't technically predict the path of the storm, and there was a sudden change in the path of the storm, and that matters, right, very much because the track and the accurate track and timing of hurricanes drive a lot of decisions like if we want to evacuate a region or not, the power grid preparation or an emergency response are all related to an accurate prediction of the storm track and its intensity as well. So in Hurricane Sandy, the lack of accurate predictions cost more than $80 billion worth of damage, and unfortunately, the lives of 159 people. So after the Hurricane Sandy, there was a kind of major attention on improving the U.S. forecasting capabilities and model accuracy. So there were a lot of work in order to improve these predictions, and a key point is to improve these models is not just having a better computer or faster computer. In addition to that, we need a We need to have a better physics in order to model the structures and the phenomena that we see more accurately. So here is a more recent kind of example that the track was predicted quite well, or at least much better than Sandy, and that's a success, right? But at the same time, the intensity was underestimated. So the intensity of the hurricane that was expected to be a category 2 or 3 ended up with a category 4. So, and that caused a lot of damage as well. So in Hurricane Helen, I believe we had more than $90 billion in worth of damage, and unfortunately, the loss of 230 people. And that, there was what is called as a rapid intensification in the Hurricane Helen that caused the hurricane that reaches the coastal areas to be much stronger. And that is one of the hardest parts of the hurricane forecasting, and a big piece of that kind of puzzle would require better understanding of small structures or small processes that happens at the ocean surface, where wind and waves and also the currents and the turbulence generated out of them are all going to interact. So in the last 10 years, this is the data for 2014 to 2024. We had like all the extreme weather events ensemble. They made more than $1,125 billion worth of damage. Unfortunately, the lives of more than 5,265 people. But much of this could have been avoided given accurate and actionable predictions. So historically, many of the rules inside these forecasting models were built from studies of airflow over flat surfaces, like wind over a smooth plate. That's great a starting point, but we all know that the ocean is not flat. It's moving and it is wavy, right? In fact, when waves are appearing, they significantly affect the structure of the airflow, and that tends to partition the total momentum flux inside a small region that is called wave boundary layer. And by wave boundary layer, I mean the region in which the flow gets affected by the wavy surface. And in our case that we are discussing here, we are considering the flow above the surface. So as I mentioned, when waves are appearing at the surface of the ocean, there is a very complex interaction among mean flow, turbulence, and also the wave coherent flow. And in the boundary layer, this will cause the total momentum to be partitioned into a mean shear, a turbulent, and a wave component. And there is a very close interaction here that cause different processes to happen at the same time. And because of that, the current understanding of the impact of surface waves on near surface turbulence and momentum flux is limited, because again, as I mentioned, this is going to be affected by different parameters, including the wind wave misalignment, the wave height, the wind speed, the wave speed. So because there are too many parameters are involved, still we are far from having a sea state dependent model, a model that can work reliably and accurately under different sea conditions. So to better understanding this partitioning of the momentum flux above the surface, we performed a set of laboratory experiments in a wind wave tunnel facility. So this facility is especially designed for air-sea interaction studies, and we are using this facility to do some kind of measurements based on what is called as particle image velocimetry. The particle image velocimetry is a flow visualization technique in which we put very small particles into the air, and we take two consecutive snapshots. We know the time difference between these two snapshots, and from one image to another image, we can see how much these particles that we put into the air has moved from one location to another. By knowing their displacement, and we know the time difference between these two frames, we can calculate the velocity. And once we have the velocity, we can technically measure different parameters inside the wave boundary layer, as I mentioned. So the particles that we are using here are fog particles. So we have a fog generator here that we put fog particles into the air, and then we use a laser to illuminate these particles and then and then take a photo of that. So this technique is called particle image velocimetry, and that's the main experimental technique that we have used for these experiments. So here is a closer look to our experimental flow visualization kind of setup. So we have a couple of different cameras and two lasers here. So I'm not going to the detail of these things, but I just want to show that what it takes to have these kind of measurements and being able to look at the small scale, the structure of the flow in the ocean or in the lab, in this case, over waves. So what I like to show is an example. So this is an example of these measurements that I mentioned. So if we look at, so this is a larger field of view and this is the smaller field of view. So we are doing the PIV in the smallest window here. And here is an example of that PIV, the way that it would look. So we have two cameras that are sitting side by side, and there are, we use them to calculate the velocity over there. So you see these fog particles. So once we have another image of the same fog particles with a very a small time difference, we can do the velocity calculation, and we can get the velocity field. So here is an example of the horizontal velocity above the waves, and we are having the color bar here. The colors shows the magnitude of the velocity. So the magnitude of velocity here, the red is around 5 meters per second, and closer to the surface, the flow is reduced, and the flow is smaller. So we have some separation that happens here, that the flow separates from the wave crest. All right, perfect. So we have done these experiments for a couple of different wind wave conditions. So we have different wind speeds. The wind speeds are varying from as small as 2.25 meter per second up to 16.6 meter per second. That is a very strong wind. So, and these are going to correspond to a wave with an amplitude as small as 0.07 up to 0.27. So here I'm showing some examples of these measurements. So once we have the velocity, we can calculate the stresses, that these stresses can be used for the larger scale models. So these stresses that we can measure in the lab can be an input for the larger scale models. These larger scale models are technically do not see the wave. The domain that they resolve and the domain that they are looking at is very large, that they technically do not see waves, but they need an information about the effect of these waves. So, and these information are called as surface stress, is one of the information that these models are going to use. So we are trying to come up with some model to better predict these surface stresses. So, and that's where the machine learning come to play for us. So there are two main components at the surface of the ocean for the stress. So one is called a skin friction drag, and the other is called form drag. So the skin friction drag is just as the wind slides on top of the wave, it causes some friction, and that will cause some drag force. So the skin friction is a component that is going to be very important at the surface. The other component is to the pressure and the shape of the wave, which is called form drag. So these skin friction and the form drag summed together is called the total stress, and that is a parameter that is going to be used by large scale weather forecasting and global climate prediction models. So but measuring them and modeling them directly, it's very challenging, and we still do not have a very reliable kind of model that can capture the variations of these surface stress surface stress drag over different sea state conditions. So, and the data-driven approach, the machine learning, is actually come to play for us in this problem, and we are using the machine learning in order to be able to better predict the distribution of this surface stress. So here is a distribution that I mentioned, that we have a surface stress that is comprised of a skin friction drag and a form drag here. So, and here is an example of another example of the velocity and the skin friction drag that I mentioned. We can calculate at the surface of the ocean. This skin friction drag that you can see here is happening or is measured exactly at the surface. So this is a case that I have no separation. So you see that the stress is somewhat consistent, is increasing, and then when I have this kind of flow separation, this viscous stress or this skin friction drag drops to a almost zero value. So, and this is the physics that is missing from the larger scale models, and we are trying to develop a surrogate model that can predict this variation. So we are using the experimental data that I showed, right? So from this experimental data, we technically can extract the wind speed, we can extract the wave speed, we can extract the wave profile, and we can also calculate the skin friction drag. So our goal is that can we develop a model that can predict the skin friction drag from just surface profile and wind speed? So, and the idea behind that is that the skin friction drag is very expensive to measure or even to model, to simulate it. It is going to be taking a long time for these measurements and these simulations, and it's very expensive. But wave profile or wind speed is something that is very cheap, so we can very easily measure them in the field. So the idea is that let's develop a model that can get the input from wave profile that is cheap to measure and then predict something that is very expensive to measure. So, and that prediction can be used for the larger scale models in order to improve these predictions. So here is the model that I mentioned. So our model is this is a CNN model that we are trying. So we are technically developing a CNN model that minimizes an L2 norm between the experimental measurements and the machine learning prediction. And the idea is that if I give you a wave profile and also the ratio between the wind speed and the phases and the wave speed, can you give me the distribution of these surface stress? So here's an example of the model input. So what we need to input to the model is basically is this profile. So once we have the profile, we can technically measure it. We can technically measure these profiles, right? And we can obtain other parameters like wave profile or the wave slope here and the phase and also the skin friction drag. So we use this one to develop the model. The model is developed, is trained on the experimental data that I mentioned that is varying from 2 to 16 meter per second. So we are using three experimental cases here to train the model. So the total data here is around 13,000 something of independent uh, PIV pairs that I call it input pairs. And out of that 13,000, we are we are separating the data to 80% training, 10% validation, and 10% testing. So we basically use 80% of the data to train the machine learning model to learn the correlation between the wave profile and the output, which is the skin friction drag. So we use the 10% to validate this and make sure that uh, um, there is no mistake in that prediction, and there is no there is no missing physics that we cannot predict. So this is important for what is called as overfit. So we can make sure that there is so the data learn the physics or the model learns the physics, but not memorize the data basically. So we use the other two experimental data here for checking how the model can generalize over uh, unseen data sets, because that's very important when we have to make sure that the model that we develop through the machine learning can also generalize to the data that it hasn't seen ever. So this is the convergence of the data of the model that shows the mean square error compared to the epoch. The epoch is technically the iteration that the training happens over there. So, and here's an example of how this model is working. So I have an example. So the first row is technically the velocity field. And this velocity field I'm putting here just to put things into perspective and see what kind of wave we are looking at. The second row here is the measurements the skin friction drag from experimental data. And the last row, the third row here is the machine learning predictions. And each column corresponds to a different wind speed. The first column is the wind speed of 5 meters per second. The second column is the wind speed of 9.6 meters per second. And the last column is the wind speed of 16.6 meters per second. So we can see that visually the model does a very good job in predicting the trend of this skin friction drag over different wave conditions. So we can see the separation and we can predict this separation very well in this model. So we can also look at some percentage error, some error metrics like L1 norm or L2 norm. So these are technically the percentage error. And if I plot what is called as probability density function, that technically shows what is the distribution of the error for individual predictions that I have in the test data set. And if I do that, I will see that I have around 20% to 30% error as the peak value of my surrogate model. But this is instantaneously, and on average, I have much better results for that. So I can now get back to this generalization idea that I mentioned, and I can look at that cases that the model hasn't seen before. So if I look at these generalization cases, I can show two examples here for the high wind speed and the low wind speed, and for both of them, the model still can predict the trend of this skin friction very well, right? So again, the second row here is my experimental skin friction drag, and the third row is the machine learning prediction, and the model is visually doing a very good job here. So I can also look at the statistics and also look at the error metrics here. And if I look at the error metrics, I see that my error has increased a little bit. That is expected because this is a data set that the model hasn't seen ever. But I have a good R square. The R square is technically what is called the coefficient of determination, and it shows how well we can predict the trend in the data. And we can predict the trend in the data very well. And these are some average values that I have here. So if I average everything together and compare to the current available field measurements and experimental measurements, I can see that I follow the experiments very well with this model, and it does a very acceptable job in predicting a skin friction drag. So this is very promising in that sense because, again, a skin friction drag or the surface stress that we are trying to predict here is very expensive to measure. So I guess I should be right at my 25 minutes. So I will have just probably uh, five key takeaways here. And the first one, as we started to talk, is that the air-sea exchange affects waves, right? And it helps to to form storms and also to shape the climate. Waves change how this wind transfer momentum through the friction and waveform drag, as we discussed. And we were able to measure this skin friction drag in the laboratory. So we measured airflow and wave motion together using some laser-based imaging techniques that is called PIV. So, and that is the main technique that we use to measure these velocities. So once we had these velocities in the control laboratory situation, we trained the machine learning model to connect the wave shape, the wave profile to near surface flow and the stress variability. And the long-term goal for us for this kind of research that we do is to make sure that we can improve the sea state dependent drag parameterization or the stress models that can help for more accurate forecast, especially for hurricane conditions. So, and with that, I thank you all for your attention. And if you have any question, I'll be happy to answer.
So, Dr. Yousefi, since we live here in California, how can your experiment or research be extrapolated into the tectonic plates, into the earthquake?
Yes, that's a great question. So it is so what we are doing is more kind of on the storm that is caused due to the atmospheric pressure. So that's more kind of hurricane that happens in the atmosphere. So it we haven't yet looked at that kind of tectonic variations, but this can be something that is interesting. But we are not looking into that problem, if
Oh,
that answers your
okay.
question.
Not yet.
Yes.
Yeah, because as you know, it's creating some tsunamis already.
Sure, exactly. Yes, that's a different type of the waves that will be generated. So, and we are not considering those tsunami, kind of generated waves. And what we are considering is just a strong wind, and how that a strong wind can cause large waves or generally waves.
Right. We have a question here. This is
Sure.
fascinating. Is there somewhere we can watch you lecture?
Uh, Unfortunately, I do not have any online lecture on this topic. There are some presentations that are available, and I guess I can share some of the links for a couple of presentations that I have done previously, and they're available in YouTube. But not the lecture-based kind of presentation. These are more kind of research-based presentation, and I will make sure to share these links with Arlene.
Thank you.
Yes.
It says, uh, someone just followed up my question. I was on the same mind frame regarding tectonic plate movements affecting waves and wind.
Correct. Yes, exactly. Yes, and that's a very interesting direction to look into that, but we haven't done that yet. So that would be definitely on something